Cauchy's mean value theorem. We have a function f of t on a domain T. We draw another function g of t on the same domain. They both go from A to B. We assume that they are both continuous on the closed interval a to b. By continuous, we mean that it has no jumps. So imagine drawing any of these curves with a pencil, but you can't lift that pencil up. That's what we mean by continuous. And by closed, we mean with the endpoints. Endpoint here and endpoint here. And further, we say that they are both differentiable on the open interval a to b. By differentiable, we mean it has no sharp turns. All throughout, these curves aren't pointy, they are smooth. And by open, we mean without the endpoints, the interior regions. Now, this theorem states that with these conditions satisfied, there exists at least one point C within the open interval a to b, such that this equality holds at that point C. And we will go ahead and prove this. Now, let's draw a third curve. We'll call it h of t, such that it is equal to f of t minus a constant r times g of t. And it is defined such that the point at its start aligns with the point at its end. This is doable. So, precisely, h of b equals h of a. Plugging for h of t, this becomes this. Isolating for r, we get this quotient. Now, recall that for Rolle's theorem, as long as we have a function that satisfies continuity and differentiability on the interval a to b, and as long as the start and endpoints are equal, then the theorem applies. Well, in our case, the start and endpoints for h are equal, so the theorem applies to it. And with that, we can assume that there is at least one point C in that interval, such that the derivative is equal to 0 at that point. Now, keep in mind that this is kind of like a linear combination of functions. So the derivative of this will also be applied to here and to here, because that's how it works for linear combinations. So we get this. Plugging in for r, we have this. And if we rearrange this, we realize that this expression can become this equality. So we have completed our proof. However, this proof doesn't really give us much of an understanding. So to build insight, let's map the functions f and g together on a fg plane, where now the domain T is parameterized throughout. So we can see the start coordinates being f of a, comma g of a, and the end coordinates being f of b, comma g of b. Now, if we take our equality and rewrite it as such, we have this. Rewriting the derivative in the df/dt notation, we get this. I have a subscript c to denote that it is at c. Let's cancel the dt's out, and this simplifies to the following. df/dg at c equal f of b minus f of a over g of b minus g of a. Now, f of b minus f of a is the distance from f of a to f of b, and g of b minus g of a is the distance from g of a to g of b. So their quotient is this line and the slope of it. So basically what this is saying is that the derivative of f with respect to g, essentially the slope of this curve, since it's on an fg plane, at a point C is equal to this slope. And right away we can sort of see this at multiple points, at C1, at C2, and at C3. So this is the geometric meaning of this theorem, but this in itself is not a proof, okay? Now, I want to make a remark. Let's recap. For Cauchy's mean value theorem, we stated that if we had two functions f and g, such that they were continuous on closed interval a to b and differentiable on open interval a to b, then there existed at least one point C in that interval, such that we had this equality. Now, if in this theorem we let g of t go to t, we'd realize that our equality would reduce to this. If g of t was just t, then the derivative of t would just be 1. Similarly, g of t became t, so t at b is just b, and g of a became t, so t at a is just a. But if we rearrange this, we realize that this essentially just becomes the mean value theorem. And further, if we let f of b equal f of a, well, this actually becomes the Rolle's theorem. Isn't that quite neat?